class, welcome to week 10, tutorial 9, all about change detection. I've added a window to the top left of the screen here, which provides a continuous zoom-in view of what's happening if I'm working in the files tree or the maps tree, and even some of the menu items here, just to help save having to flip around, zooming in and zooming out. And then of course you get to look at me in the bottom left-hand corner and see where things are going. What I've done is I've already added a PIX file into the Files tab. It's called bothyears.pix, and it has two different layers. And the two layers are classified imagery from one in 2014 and the second layer in 2019. Same geographic area. Let's go take a look. So we're going to take the 2014 data, we're going to view it as pseudocolor. And we're going to take the 2019 data and we are going to view it in pseudocolor. And I'm going to go back to the maps tree. And if I take the 2014 data and I expand, you can see that we have water, cloud, shadow, disturbed, and vegetation classes. These were produced very quickly with a very rudimentary classification. The precision of the classification isn't the goal of this lab exercise. But it's all about how do we compare this one with the data set here in 2019. So let's expand the 2019 as well to see what categories are in there. Whoa, we have here, as we can see, all of the values up to 255, which means that we're looking at all of the full 8-bit potential. However, I know that I've already classified this to the same 5 categories, so I'm going to right-click on the layer, head on down to Properties, and I am going to, under the image, source image tab, under the pseudocolor table, I'm going to select the current file, and instead of this temporary layer, I'm going to choose the classified PCT as the color scheme that I want to use, and I'm going to hit OK. This looks much better, but we still have a category 0, and all of these categories 6 through to 255 that we probably want to clean up. So we can easily right click on here, head on down to Edit PCT. We can select the 0 category and hit Delete. Then click on 6, scroll all the way down to 255, holding down the Shift button, click on the 255 row and hit Delete. Okay, that's good. Apply. We'll close this. We'll zoom out to the full extent so we can see what we're looking at. And then I'm just going to, to make this a little bit easier, I'm going to rename these categories. So when we're looking at them, it's a little bit cleaner. Cloud, shadow, disturbed, and vegetation. So now we have a 2014 and a 2019 layer in the same PIX file. They've both been classified the same way, the same coloring scheme just to make it easy on us, the labels to make it easy on us, but the land cover digital number, the code that's in the file, is also consistent and the same. Let me show you what I mean by that. If we were to zoom in on a small area of this image, I'm currently looking at 2019, the pen is next to it. When I click on the green area, notice that it's category 5. If I click on this gray, this is category 2. If I click on over here, on this disturbed area, this is category 4, and so on. So those categories are in 2019. If I turn that layer off for a second and I put my pen next to 2014 and I click on the green, notice that I'm also category 5. The dark gray is shadow, which is category 3. And the disturbed area is category 4, and water is category 1, and so on. So the two layers are classified in exactly the same way. Zoom out to the full extent. I'm going to turn both of these back on. We can also go to the View menu and go to Visualization Tools, and we can choose to swipe. And if we go all the way over here to the left, notice that we're looking at the 2014 image. And as I slide across to the right, we add the 2019 over top. So same geographic area, major similarity in the water bodies, but the disturbed area obviously changing. There's issues with cloud and shadow, but we have two different classified images of the same geographic area. We can now do a change detection to find out what's different between these two data sets. So to do that, we're going to go up to Tools. Under Algorithm Librarian, we are going to look for an algorithm called MAT, which is short for matrix. And if you've used it before, you might find it under your favorites or your recently used algorithms. Otherwise, we can click on Find, and we can type in MAT and hit Find Next. And mine finds it right away. Yours may find something different. If it's not finding matrix on your first click, hit Find Next again until it cycles through the various tools and finds it for you. And then we can double click on that algorithm to open up the window that allows us to parameterize how that thing's going to run. We can then close the Algorithm Librarian window because, well, we don't need extra windows open. As input, we can expand the input layers. We need to provide those two different categorical layers, 2014 and 2019. And as an output, I'm going to write the layer to the viewer as a pseudocolor image. You're more than welcome to write it to a PIX file. It saves you having to save it as a PIX file later. However, for demonstration purposes and to not clutter my disk, I'm simply going to draw it in the viewer for you. Then under the Input Parameters tab, we need to identify that it's category 1, 2, 3, 4, 5, separated by commas, that we're putting as input, and the same categories on the second image. We want the reporting to be written to the log, which is going to be on this tab when we're finished with the output. When all of this looks ready to go, we're going to click Run, and then we're going to wait. There we have it. So before we look at the image that popped up, and I know it's nice and colorful, and the first thing we want to do is go and see what's there, we can also click on the log button to see what the output is like. And I suggest you take this, copy it, and save it so that in case you accidentally close this window, you don't have to rerun the analysis. But I'd like to point out some key pieces that are on here for you. The first is that it tells you that it ran matrix analysis. It tells you the date and the time that the analysis was run, and it tells you that the first input layer was an 8-bit unsigned integer classification layer, and our second band is also 8-bit unsigned data. So it tells us that the columns represent the information that was in the first image, and the rows represent the information that is in the second image. And if you then saved the output, it will write that to channel 3. The coincidence matrix in this sense here is simply giving us a key that is going to allow us to interpret the output categories. So again, remember we have categories 1, 2, 3, 4, and 5 from the input image channel 1, and 1, 2, 3, 4, 5 as the input from the second image. And then each of these unique numbers, 1 through 25, are the pairwise combinations that those categories can produce. So we want to remember these numbers. Those numbers are the same 1 through 25 that we see down here that tells us how much of one category overlaps with another category between the two different images in the input data that we provided. However, this is a very awkward way of interpreting the results. So what I've done is I have created an Excel sheet that makes this much easier to look at. And I've taken sort of the liberty to already sort of populate it with the unique category numbers 1 through 25 that tell us what the 2014 categories versus the 2019 categories are. And I've colored them and numbered them so that it makes it really easy to remember what we had up here in our map tree in this output. Now, what we need to do is look at this output class number 1 and realize that there are 82,741 pixels that meet this condition. That is, water that was labeled as water in 2014 remained as water in 2019. So we can highlight that value, hit Control C to copy it, And we can come down here and hit Control V to paste it into the table. And we can do that for each of the unique combinations and fill out this table. To save us some time, I've already done that. I've got that on this tab over here. And notice that we have all of the values that came from this pixel count nicely into this table. What I've done then is I have summed all of the values across the rows over here. So this is the sum of water, cloud, shadow, disturbed, and vegetation sort of across 2014, but what existed in the 2019 data set. So in 2019, there are 108,855 pixels labeled as water. There are 150,649 pixels labeled as cloud, and so on. Similarly, the sums down across the bottom are the total number of water or cloud or shadow or disturbed or vegetation cells that existed on the 2014 data set. And then these numbers inside tell us which ones changed or remained the same. This is the total of all of the pixels. It's the total number of cells in the image. So we can take any of these numbers and we can convert them all to areas. We know the area of a pixel. This is Landsat data. It's 30 meters by 30 meters. So we can take 30 meters times 30 meters times this number of pixels, and instantly we have an area in square meters. We can then divide by 10,000 and get that value in hectares, or some measure that's meaningful at the scale that our data is being presented at. This here, in this matrix form, is much easier to say, well, in 2014 I had vegetation, but in 2019 it was disturbed. So I know how many vegetation pixels became disturbed. I know how many pixels were previously disturbed but are still showing as disturbed in 2019. I know how many pixels were shadow in 2014 but show up as disturbed in 2019. No cloud pixels in 2014. And some water pixels became disturbed. So again, the classification isn't perfect, but this matrix can very quickly now tell us how many pixels or what area of one land cover type transitioned to something different. And of course, the values here along the main diagonal didn't change at all. This is persistence. This is water remained water, cloud remained cloud, shadow remained shadow, disturbed remained disturbed, and vegetation remained vegetation. So anything that's on that main diagonal means no change. Everything off of that main diagonal means that there was change. So depending on what question you're asking, you can then look at various combinations of cells to summarize the areas based on change. We can then take this knowledge and we can go to the map that was produced. And again, there are a whole series of categories here that we don't need because we know that there are only 25 output categories. So I'm going to right click on this layer, go down to Edit PCT. I'm going to get rid of category 0. And I know that I have 25 categories. So starting at row 26, holding down Shift and selecting the 255, I'm going to delete. And then I'm going to close that window. So now we have random colors assigned to all of the various combinations of change that happened. There's the whole map. I can then zoom in, let's say down to here, and if I look at this category, this is category 1 down here. And category 1, if we bring back our Excel sheet, category 1 was this water remaining as water. We can see that there were 82,741 of those cases, but any time that we see this green, it means that water that was there in 2014 remained as water in 2019. So it helps us interpret what we see. But what about this pink color here? This pink color is category 20. Let's go back to our matrix. Category 20 is something that was vegetation in 2014, but became disturbed in 2019. So this is the area that we're really interested in. So category 20, let's make it something for boating so that we know where that happened. So all of those areas that are showing up black are areas that were vegetated but became disturbed. But we know that there are other categories that also became disturbed. Let me bring that table back up again. We know that category 19 was disturbed but became disturbed, so we're not going to worry about that one because that's persistence. But we have category 18 that was shadow and is now showing up disturbed. We have category 17 that was cloud and is showing up disturbed, and category 16, which was water, and is becoming disturbed. So really 16, 17, 18, and 20 are the categories that I'm interested in terms of what became disturbed. So we can go to 16, we'll make that one black as well. 17, that became disturbed, and 18, we'll just make them all black. So those are the areas that are black that became disturbed. Everything else is some other combination of change. Maybe there was shadowing or clouding or something that went on, but these are the areas that I'm most interested in. Then I could take these categories, 16, 17, 18, and 20, and produce those using Easy Modeler into a binary result that showed me change, not change. Or I can very quickly just turn all of these check marks off. So we're not showing those categories. I should turn off the categories down below as well. So now we have a map of where change occurred. Post-classification, change detection. Using MAT gives you the tabular results. We can rearrange them to make them a little bit more useful to look at. And then we can look at it graphically, and we can figure out exactly what happened by looking at what the output cell number is and comparing it to our transition matrix that we have here, and very quickly have the area, in this case here, the number of cells that were related to that type of change. If you're not really clear on how to calculate the area, let's put in here, just for example, the number 30, which is the dimension, the spatial resolution of a pixel. We can then go in here and say that we want to do equals this times the same value again times that. And this is in square meters. That number is a little bit nutty. We can divide by 10,000, and now we have a value in hectares. So I'm just going to very quickly redo the analysis, but I'm going to save the output as a PIX file instead. So back to Algorithm Librarian, MAT, close the one behind, choose the two layers. I'm also going to look at it in PCT, but I'm going to save the output into my tutorial 10. I'm going to call this MAT output, all in caps, because that's something that is going to stand up nicely for me. I'm going to hit OK. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 log. And I'm going to hit run. Okay, so exactly the same result that I had before. Notice that I have this result here as an output into the viewer, but I'm going to hit this white tab to create a new focus sheet, and I'm not going to save any of my changes. I'm going to pull up a Windows Explorer that has my mat output PIX file in it. I'm going to drag it in, and it's showing it to me in grayscale. Well, maybe I don't want it as grayscale. I can always look at it in pseudo color, go back to maps, remove from area the one that's in grayscale, and I have my map that has the categories from the MAT output. Now, if you remember, we also had a series of categories that we want to save. So if I bring this over, we can see that we have categories 16, 17, 18, and 20 that are disturbed. I want to create an output that has those as ones and everything else as no data or zeros. So 16, 17, 18, and 20, those are going to be coming from this input layer, but I need somewhere to write the output. So back to the Files tab, right-click on the PIX file, head on down to New raster layer, and we're going to add one 8-bit layer. Okay, so now there's a second layer here. Let's just rename it. This is going to be binary. Okay, so we're going to read in from the first band, and we're going to write our results to the second band. We're going to head up to Tools, Easy Modeling. We're going to have here already selected the PIX file that we're working with, and now we're going to enter some code. And just so that you can see it better, I'm going to slide this over here so you can see my typing a little bit bigger in the zoom window. I'm going to say if %1, so if that's band 1, that's our input layer, is equal to 16, or if %1 is equal to 17, or %1 is equal to 18, or %1 is equal to 20, then we're going to indent, %2 is going to become equal to 1. So at every location where the input is either a 16, a 17, an 18, or a 20 is now going to become a 1, and then we want to indicate what we do otherwise. The key for that is else %2 becomes 0, and we type in end if to close the whole thing down. So we check if the first band is any of those digits. If it is, the output is going to be a 1. Otherwise, it's going to be a 0, and we terminate. I'm going to click Run. That went quickly. I'm just going to minimize that, and I'm going to take this modeling result, and I'm going to view it in pseudocolor. Back to the Maps tab. I can turn the original one off, and notice that if I were to zoom in here and click on any of this green area, my value would be a 1, and if I click out here, the pixel value is NA, or no data. So now we have a nice binary layer that we can use anywhere that we want, and if we don't want it in this PIX file, we can always save it and transfer it into a different PIX file and use it moving forward. So that's all there is to it. We can create classifications. We can then test to see whether or not something changed, and if it did, then we can extract the pieces that we really want using Easy Modeler and a simple if-then-else statement, and produce any combination that we want. And if at the end we didn't want these green cells to be 1s, when we created our code, then we could have said that the output is going to be, let's say, category, maybe we like the number 55. And maybe we didn't want 0, otherwise we wanted 4 otherwise. Well, we hit Run, and then notice it overwrites the data set. But now, when we look at our output data, this orangey stuff is category 4, and this blue stuff is category 55. So we control every aspect of what's happening with the data. There is no sort of cover your eyes and hope for the best. We decide which categories go in and which categories come out and what we call them. And there we have it. Have some fun. Talk to you soon.